Then there is two parts of the slide. The first part is the background. I will introduce the Sangfor Cloud Security Pool and the traffic steering problem. And the second part is the policy-based routing and the SDN-based service function training. It is two different ways to solve the traffic steering problem. At the second part is the whole solution of the SDN-based service function training, including the deployment framework, workflow, flow table design, realization, optimization of the proxy, some paths, and the text result. And finally, Yi-Yang will introduce the network function header. Okay, first let's take a look at the CSP. It's Cloud Security Pool and CSP for short. Okay, let's see the picture. Okay, let's see the picture here. At the top is the client network. There are many VM physical hosts here. And in the middle is the physical core router. It will steal the traffic steal the traffic from the client network to the outside network. Outside network is maybe the internet. And at the top of the figure is the CSP. CSP here is the cluster of virtual network functions. What is virtual network function? In Sangfor virtual network function like this, the VMGAF, they are all at this place. VMGAF is the virtual next generation application firewall, and the VSSL is the VPN with SSL and IPsec, and the VAC is the virtual internet access management, and the VAD is the virtual application delivery. It's used for load balancing, and the VWC is the virtual WAN optimization, and VDAS is the virtual DV auditor, and there are two more. And then there is one more important component in the CSP is the CSSP. It means the Cloud Security Service Platform is the management UI. Okay, then let's talk about the service function training. We define the service function training like this. It is used to steer the selected traffic to passing through some virtual network functions in order. And let's take a look at one example here. The traffic is generated. Oh, it's out of power. The traffic is generated from the client network. It comes at the physical core router and is steered to the CSP. And in the CSP, it passes through the service function training. The service function training here is VMGF, VAC, VAD. The traffic passes through these three components in order. And then it comes back to the PCR, and then it will direct to the outside world. And the SFC is this part. It means this part. If without the CSP, the traffic from the client network will go directly to the outside world. So here I will introduce the probability-based routing. It is the original solution of the CSP to steering traffic. Okay, then let's see the picture again. The traffic is generated from the Tenant2 network. The traffic comes at the physical route. The physical route uses the PBR to steer the traffic to the CSP. And the core router and the edge router and the vSwitch here are also the virtual ones. It means they are the software version router and switch. Then the core router here will use PBR to classify the flows and direct them to the different edged router of different tenants. Each tenant has one edged router, and it used the edged router to to realize the SFC functions. And here we can see that the SFC path is VAC, then is VSSL, then is VMGAF. Okay, then after finish the SFC path, the flow comes back to the edged router. And the edged router used the default route to steer the traffic to the core route. And core route used the default route to direct it to the physical route. And the physical route also used the default route to steer the traffic to the outside world. Then here we focus on this part. Each time the packet passes through one VMF, it comes back to the switch. then it has to go back to the edge router to find the next hop of VMFs. So between two VMFs like VAC and VSSL, there is 4 hops. And in the proxy-based routing solution, the SFC path is a little long. And here we compare the proxy PBR-based and the SDN-based SFC solution. The picture at the top is the PBR-based, and the picture at the bottom is the SDN-based. We can see that the PBR-based solution has obviously disadvantage, like more hops, and the performance is not good enough, and the flexibility is bad. It can only use the destination IP to steal traffic. Opposite, the SDN-based service function training with OVS DPDK is advantage is also obviously. It needs less hop, its performance is better, and is more flexible in traffic steering and flow entry management. Okay, now let's see the real deployment of our solution. The picture here, this is a physical host, and the VMFs are deployed in virtual machine, in VMs. Okay, then here, the example is like this. Our CSP is deployed in the transparent mode. The traffic, the example here is the traffic from the outside world to the client network. So the traffic comes into the CSP by this WAN port, and it passes through the VMFs. This here is 3 VMFs in order, and leave the CSP at the LAN port, and then it comes to the client network. Okay, the SFC path here is VMGF, VAC, and VAD. And here, if 2 VMFs are at the same host, we don't use the network function header to make the performance better. And if the 2 VMFs are at different hosts, we will use the NSH, and we will talk about it later in the slides. Okay, then is the flow classifier. We use 5 tuple and the VLAN ID as the flow classifier. The 5 tuple is source IP, destination IP, source port, destination port, and the protocol. It is used to classify the flows, match the flows to different service function chain. And we also use the ONOS, a type of SDN controller, to dispatch the configuration and the flow entry to the OVS by OVS DB and the OpenFlow. This slide shows the framework of our SFC solution. It consists of 3 planes. At the bottom is the data plane. We used OVS and DPDK here, which supports the newly standard network function training. And in the middle is the control plane. Is ONOS and SFC application here. The SFC application realizes 2 functions. It's the basic network function and the SFC function. At the top is the management plane. It means the CSSP, the UI. Then this picture shows the workflow of our SFC application. Okay, I will talk about it in detail. The configurations like the creation or updating of different resources like tenant and classifier comes at the ONOS by the RESTful API. It will dispatch to the different resource management and update the related store. And the store update events will capture by the ONOS. And this event, and the ONOS will notify the SFC management about the related events. Okay. Then the events are in queue and waiting for being processed. And some other events like exception events or device online and offline events also in queue at this entry. Okay. Then these events are dispatched to different components for processing in more detail. There are 2 main events. One type is the basic network function related events. It's about the tenant, the synchronization, the device, and configuration events. It will influence the configuration and the flow entry of the layer 2 and layer 3 network function, like the ARP table, learning table, FTP table. Okay, then the second type of event is the SFC function chain related events. They are bypassed, classifier, proc group, proc chain. It will influence the tenant table, it means the FCC table. And then finally, we will use the OVS DB and the flow rule install function to send the configuration and the flow entry to the OVS. Then here comes the flow table design. We had 7 table here. 6 table is for the basic network function. 1 type of table is for the service function training. And this type of table has 200 tables. Okay, let's see them. First is the input table. It is used to classify flows and send them to different next table. It's the entry of all packets. And then is the tenant table. Tenant table, you realize the SFC traffic steering function. We assigned table 10 to table 210 to different tenants. Each tenant has 1 SFC table. And then is the FTP table. FTP table is forwards packet to next hop. The matched field is MAC address. And then is the ARP table used for ARP suppression. And the flag table. In the flag table, we shove interface into different flag area and generate related broadcast table to reduce the flag. We use the group table as the broadcast table here. And then is table 214 is the learning FTP table. It learns forwarding rules from the FTP table and ARP table to avoid unnecessary flags. And finally is the out table. It's no use, it just reversed for expansion in the future. Okay. Then let's see the SFC project. Each SFC project has 2 functions. The first function is decap and record. And the second function is track the hash table and encap the packet with the network function header. The picture here is one example. The data plane at the bottom, and then here is the VMFs. The proxy is here. We can realize the proxy by hard-coding it into the OVS, or use the flow entry to realize it. Okay. Then here, the first function of the proxy, the packet comes from port 1 to the proxy. It decap the packet here is with the network function header, and the proxy decap it. Then it records the mapping of the file table and VLAN ID and message header in the hash table. And then the packet comes to the VMFs and come back to the proxy from the POC 2. Then the proxy will derive file tuple and the VLAN ID from the packet and do the hash computing. And then the proxy track the hash table and find the SPI and SI. And it minus the SI by 1. Then it used the SI and SPI to encap the packet with the network function header. Okay. Then there is 2 ways to realize these 2 functions. First is by hard coding, and we have to maintain the hash table by ourselves. And the second way is by flow entry. When flow controller generates the flow entries, it knows the mapping of file table, VLAN ID, and the ingress port and the network function header. So here we compared these 2 ways of the realization of the project. The first way, hard coding, and the second way, by flow entry. And finally, after discussion, we choose the second way because we want to keep the OVS code consistent with the community, and we also want to keep the data plane as stable as possible. So we prefer not to change the code in the OVS. And after the realization, let's talk about the optimization of the SFC project. Okay, we found that the MS network function header encap and decap will decrease the performance by 30 to 14%. And we also find that if 2 VMFs are in the same host, the network function header encap and decap is unnecessary. So let's see it in more detail. And here, if there is in this situation that two VMFs at the same host, after the packet pass through the first VMFs, it comes at the OVS, and then it will be encapped with the network function header. Then it finds that the second VMF is at the local host. The network function header is decapped before it will send to the second VMFs. So we found that this part is unnecessary. So how we optimization? We cut this procedure. And then if two VMFs are at the same host, it will, the packet will send directly to the second VMFs. And if the next VMF is at the remote host, it will encap with the network function header and send the packet to the VXLAN GPE terminal. Here we showed our work on the ONOS, OVS DPDK, and the OpenFlow. First is our change on the ONOS, including the basic network function and the SFC function, their logic. We also realized the NSH function, change the make the group table to support OpenFlow 1.5, and make some bug fixed. And the change on OVS merely focus on the bug fixed. The last is the change on OpenFlow. We keep we keep the network function header related code in OVS unchanged, and we changed the code on the ONOS logic. It's a third-party library to realize the OpenFlow for ONOS. Okay, here is some text result, and this is the environment setup. We have finished our work, and we can see from the table that the high ability, the recovery time, the latency, and the throughput is well enough. The performance and the function of our SDN-based SFC solution is good enough. Okay, then let's welcome my partner Yi-Yang to introduce the network function header. Hey, please.
No?
Hello?
No worries. No? No?
No.
Network service header is IETF standard RFC. It is for service function chaining. For servers test, NSH, decap, and encap. NSH encap and decap will reduce performance by about 20%. So performance is a big challenge. Actually, Sangfor use case just use NSH and VXLAN GPE in cross compute node case. For Sangfor's use case, they use VXLAN GPE and overlay. Here is the packet format. VXLAN GPE is a VXLAN extension. It uses some reversed bits. It defines next protocol and some flags. For current OS NSH implementation, we use NSH MD type 1. Here is a header format. Total size is 24. In this header, we have TTL, MD type, next protocol, service path identifier, service index, and cortex header. In cortex header, we have C1, C2, C3, C4. This is just to show the specific service chain. We use service index to indicate the hop index. For first hop, it's 255, and the second hop, the service index is 254. The second one is 253. Here is we and NSH stuff in OS. We and many match fields and some new actions. You can reference them to make sure use them correctly. Especially to mention, you cannot match inner fields before decap NSH header because OS flow parser just parser outer header and NSH header. Actually, we have some no issues in current OS implementation. The first one is encap action will be done twice in group table. This bug has been fixed by Yen. For performance, it's a very big issue because we use NSH and VXLAN GP for every hop. So that's a big challenge. We need to improve. Currently, many VNFs cannot support NSH, so we have to use NSH proxy. It's a SFC proxy. So this proxy will lead to more performance loss. In all the Linux kernels, actually OS will auto-config and load in-kernel VXLAN modules and UDP tunnel modules. But these modules cannot handle VXLAN GP package, so it's another issue. We also have a packet checksum issue if your inner packet size is 1,500 and your VXLAN GP interface MTU also is 1,500. For MD type 2, actually current implementation can set MD type 2 and set TLVs in encap action, but it cannot change TLVs and match TLVs. In OpenStack networking SFC project, it doesn't support NSH yet. So for orchestration layer, it's not ready. Okay, I'm done.
Let's thank our speakers. All right, we used up most of the time, but if anybody would like to ask one, we have time for one question. Well, thanks again.
Sorry.
Oh,
yeah, just a quick question. You mentioned a 20% performance degradation. Is that worth? That was with MD type 1, right? Metadata type 1 in your NSH header.
I didn't quite get the beginning. Did you understand the question?
No. What do you mean?
Let me rephrase.
Maybe you should. Can you speak a little closer to the mic?
Sure. So You mentioned a 20% performance degradation, and was that with MD type 1 in your NSH header? And do you expect that performance degradation to increase or to improve when you move over to MD type 2?
Did you get it?
Sorry, I didn't get your question.
Okay.
You mean?
Okay, so he said that with MD type 1, you saw a 20% performance degradation.
Yeah.
Would you expect it to increase with MD type 2?
No. Actually, MD type 2 is for different use case. It's
Okay.
not for performance.
Okay. Yeah. Okay. Yeah, I was just wondering because the MD type 1 you said is fixed.
Yeah.
Your metadata's length is fixed.
NSH MD type 1, you just have fixed header size for metadata. But for MD type 2, you can include maximum 256 TLVs. That's different.
And we expect that will degrade performance even more, right?
Yeah.
Okay. Thank you.
Let's thank our speakers one more time.
Okay.